In this video, we're going to talk about text classification with neural nets, but actually not with LSTMs, not today. Today, it's going to be text classification with convolutional neural networks. And I think it's super cool because, it wasn't obvious to me at first how you would take the convolutions that we do on 2D images and apply it to text, but actually you really can. And you could take all the things that we've learned, all the intuitions we have with processing images and use it on text. So things like max pooling totally applies to text. And this is really practical. A lot of people do this in the real world. This is something that Facebook uses to do a lot of their text classification. And also, in order to do it, we're going to learn about embeddings. And I think embeddings are one of the most interesting, coolest topics in all of natural language processing. And we'll go deeper on it in a later video, but the first time you see embeddings, I think it's pretty cool. So, the big problem with using neural nets on text is that it's kind of hard to get things from text, which is arbitrary length strings, into the API that I'm always talking about, the specific API for any of these neural networks, which is basically a fixed length string. One of the ways to do it, the kind of most common way to do it circa 10 years ago, still super popular, is called bag of words. And we covered that in the first video that I did on text classification without neural nets. And this is, you might recall, just taking each word and counting how many times it occurs in each document. So you basically transform this string into a vector where the length is the number of words you have. And the problem, of course, with this is that you completely lose the order of words. So in most languages, definitely in English, the order of words actually matters. And so dropping that order, it's kind of amazing that classification can work at all. And certainly it can't work as good as it could. So there's another transformation that we talked a lot about in the previous video where we're generating text with LSTMs, and that's using the individual characters. So basically one-hot encoding every character in the text. And that kind of makes intuitive sense as like a nice transformation, and we can actually pad out the characters to make all the text a fixed length of characters. But the problem there is that actually in English, spaces matter a lot, right? The concept of word is a pretty useful concept that we might want to pass into our neural network. And so by just passing in each character as a character encoding, we're really making the neural network learn a lot about language. So it might be too raw, too extreme, unless we have truly massive amounts of data. So for best results, we really want something in between. And that's where word encodings come in. Here you have an example. We have the sentence, "I love this movie." And we're transforming each word systematically, deterministically, into a set of numbers. And in this case, we're transforming it into 4 numbers. So the word "I" always transforms into the same 4 numbers. The word "love" always transforms into the same 4 numbers. And we can do this with longer vectors, right? So in this table, we have each word that we might have seen in our vocabulary, and then the transform that each word gets turned into. So if we don't want to calculate the embedding ourselves, we can actually use some of the pre-computed embeddings. So word2vec is a famous one. Today we're going to use the glove embedding, and this is something generated by Stanford on a huge set of data. And it actually has some amazing properties. They're incredible properties that would be worth a whole video to explore more. You can do some research on your own. But basically, if you take the actual embeddings, so these are the actual numbers for woman, and you subtract from those numbers the set of numbers that got encoded as man, and then you add in the set of numbers for king, you actually get the set of numbers, or a set of numbers that's very close to the numbers for queen. So this is really incredible, and what it shows is that these embeddings are actually encoding some semantic information about these words. And so actually using these embeddings, using these numbers that are pre-generated by Stanford in this case, that you can download, can often make your models perform even better than trying to calculate these embeddings yourself. This is kind of like transfer learning, but for words, if that makes sense. So once we have these embeddings, once we've transformed all of our words into these fixed length vectors, and remember that it has to be a fixed number of fixed length vectors, so we actually have to transform, we have to add padding words to make each document the same length. Once we've done this, how do we turn it into a classifier? How do we make a convolutional classifier? What would that even mean? So I think it's useful to go back and review what we meant by a 2-dimensional classifier on images. Right, so remember that with a 2D classifier, we would take an input and then we would multiply a weight by a block of values, and we put the weighted sum of that block into a subsequent output image. And then we move that block over by one or over by a stride, and then we do that same computation with the same weights, and then we fill in the next block over in the image. And remember that we could actually have multiple outputs. And what multiple outputs would mean is that we start with the same image, but we use different sets of weights. And so as we slide the block over, we're actually in each case multiplying it by different weights and then outputting multiple images, or sometimes they call it multiple channels. And then you might have missed, a lot of students kind of miss this, how this exactly works, but you can actually take in multiple inputs. So if we had 3 input images, in this case, actually, if we have a color image, we might turn it into 3 channels, a red channel, green channel, blue channel. We can do the same thing with a convolution. And in this case, we actually have 3 different blocks of weights, and then we sum the result of the convolution of each block of weights on each one of the input channels, and we have a single output channel. So we can have multiple inputs and multiple outputs in this way. And now on text, we actually don't have a 2-dimensional thing, we have a 1-dimensional thing. So here you can think of that 1 dimension going across as the pixels of an image. And you can think of what I have as the y dimension here as actually the different channels. So instead of taking a 2-dimensional block, we take a 1-dimensional block across the pixels. So say in this case it's length 3, and we take a weighted sum of each of the pixels. So in this case we would have 3 weights, and we multiply them by one of the channels, and we take that weighted sum and we fill in an output. And then we move that block one step over, or a stride step over to the right, and then we do the same weighted sum on the new data from our embedding, and we fill in the result in the next channel or the next pixel over. And we actually run that weighted sum across all of the channels. And we take the sum and we fill in one value. And now we could have multiple dimension output or multiple channel output. And in that case, we would just have different sets of weights for each of the channel that we're outputting. And in this case, we're actually going to learn the weights for all these different channels. And what this is going to do is combine the words into smaller values. It's in some sense going to give us information, or it's hopefully going to learn information about pairs and triples and more of words. So you might remember with images, we would do this thing called a max pooling operation, where we would take a block, typically a 2x2 block, and we'd find the max of the pixels in a 2x2 region. Well, there's actually a really obvious 1D analogy to this, where we look at any particular channel and we take, in this case, not a 2x2, but just a length 2, or it could be a different length block, and we find the max, or in average pooling case, we find the average. And with images, this gave us a chance to kind of find longer range dependencies with our convolutions, and with tests, it's exactly the same thing. So we can actually build up the same structure that we had for classifying digits with 2D operations, with 1D operations on our text. So it's typical to have a convolution followed by some kind of pooling, followed by a convolution, followed by some kind of pooling. So let's go to the code and see how this really works. As usual, go into the videos directory in ML class, and then go into cnn-text. And then open up imdb-cnn.py. And let's take a look at what we have. So, the first 11 lines are just importing various libraries. And then lines 17 through 24 basically sets some configuration parameters. One configuration parameter to point out here is the vocab size. So that's 1,000, and that's because our embedding has to take a fixed length set of words and figure out what they map to. So in this case, we can only handle 1,000 words. So any words that are less frequent than the top 1,000 are actually going to get removed from our data. So line 26 loads in the IMDb data. So I have an IMDb data set that's actually quite famous, and these are basically movie reviews. So if you run download-imdb, you'll get lots of movie reviews, and the idea is to classify just from the text of the movie review if the movie was positively reviewed or negatively reviewed. And neutral reviews are actually removed. So all these reviews are quite clear if they're positive or negative. So we're going to magically load that data into x_train, y_train, x_test, and y_test, which you might remember from MNIST is basically the training input and the training target, and then the validation input and the validation target. So in this case, the y value is actually only 0 or 1, basically negative or positive. There are no neutral reviews in this data set. Lines 28 through 31 basically turn this text into numbers. So the first thing that happens is line 28 sets up a tokenizer. And the important parameter passed into the tokenizer is the number of words that we're going to look at. So anything outside the top 1,000 most common words is going to get removed. And that was set in config.vocab size. Line 29 does this actual fit on the text. And in this case, it's x_train that we fit on. So that looks at what actually are the most popular words. And then lines 30 and 31 do the transformation from the actual strings into numbers. And in this case, it transforms them into a one-hot encoding based on the top 1,000 words. So the rows here are the individual words, and the columns are words in the text. Lines 33 and 34 take the xtrain and xtest values and they actually pad out the sequences. So this actually adds essentially empty words to the text, so the input to our model is all the same length. So there is a maximum length that we have to give to this, and that's in config.maxlen. In this case, the longest review that we're going to consider is a 1,000-word review. So we could try change that to a longer value and see if it matters. But in this case, all reviews are going to get truncated to 1,000 words, and we have to set that to something. Line 36 sets up this model, and then line 37 actually does a new kind of layer that we haven't seen before called an embedding layer. And so this embedding layer takes as input the vocab size, because each word is going to be an input to this. So we're going to take the top 1,000 words and find an embedding for them. And then the second input is the embedding dimension. So the bigger we make the embedding dimension, the more numbers we're transforming a word into. So if this is really big, our model might get too complicated, it might overfit or something like that. If this value is too small, then we might lose the information in the words and our model may underfit the data. Then we had a dropout layer to prevent overfitting. You probably remember this from some of the image-based neural networks we were building. So then we had a conv 1D layer. This is just like the conv 2D layers that we're using on digit recognition or fashion recognition or any kind of image recognition. And again, we have this filters parameter, which is how many output channels this convolution layer has. And we also have a kernel size parameter, but instead of the kernel size being 2 numbers, it's 1 number because it's only a one-dimensional convolution. Padding equals valid basically means that we do no padding to our convolution, so it's actually going to shrink our output a little bit. And then activation equals relu means that we run a relu activation function at the end of this convolution. Then we have a max pooling layer, and then we go back to another convolutional layer, and then another max pooling layer. And then you might remember we do a flatten, and then a dense layer, and then finally one more dense layer. So this is just like the digit recognition classifier that we built earlier in this series. Now, because our model actually only outputs 1 number as opposed to 2, but we're doing a 2 classifier, so there's positive and negative, we have to use binary cross entropy to properly calculate our loss as opposed to categorical cross entropy. We also use the atom optimizer, as we've mostly been using throughout these classes. And we also want to output the accuracy metrics so we know how well our model's doing in sort of a human readable format. Then our last line calls model.fit with our xtrain, and this is the input matrix. And ytrain is the classes, positive or negative sentiment. Our batch size is set in our configuration, and our epochs is set in our configuration, and we also pass in our validation data. Let's run this model. So for example, here the validation loss is starting to go up and the accuracy is starting to go down, which means that this model may be overfitting. And one thing to really be aware of is that the embedding adds a lot of free parameters. So if we look at the actual structure of this model, there's a lot of parameters contained within the embedding itself. So there's some extra things that we've made it learn. So it might be interesting to try to use the embedding that we can download from Stanford's website, the glove embedding that I talked about earlier. And you can see an example of where to do that in imdb-embedding.py. So at the top it tells you the first thing you need to do is actually download glove from the URL that I give you. So we'll go ahead and do that. So embedding is actually super similar to imdb-cnn, but there's a couple new lines I inserted here where we open up this embedding file, which is actually in a super simple format, and we pull out the words and we pull out the numbers that these words correspond to. And then we take the embedding matrix and we look inside the words that we have in our tokenizer, and we actually set the values inside of our embedding layer to be exactly the embeddings that we got from glove. And then in line 61, when we add our embedding layer, we actually set that trainable equals false. So we tell it its weights matrix by saying weights equals embedding matrix, and then we set trainable equal to false, which reduces the number of free parameters, makes our model train faster, and potentially overfit less. So I really like this because we're using the fact that someone spent a lot of time training these values, and they can make our model better and everyone else's model better. So we can run this with python imdb-embedding.py. Cool, so we learned about two really important things. The first is we learned about how to use word embeddings, which is practical all over the place, not just in this application. It's super cool. And this is just one example of how to do it. And the second is we learned how to take convolutions and pooling and all the things that we did on images and apply them to text in a really practical way to get high accuracy on the IMDb sentiment dataset. In the next video, we're going to learn how to take LSTMs and apply this to the same dataset.